Hello, everyone. My name is Fenris Liu, and I'm doing research in Professor Anne McCoy's group. And my talk today is about utilization of neural networks for diffusion Monte Carlo. So you guys probably all heard the term neural networks or artificial intelligence. And even if not, you guys probably been using it every day in your daily life. Things like natural language processing, machine translation, and facial recognition. But have you ever thought maybe it can help us solve more sophisticated problems, things like quantum mechanics? And in our group, we study the vibrational and rotational spectroscopy of molecules. And in order to do that, we need to solve the Schrodinger equation for molecules, which is impossible. But that's okay because we can run simulations to get pretty good approximation to the real analytical solution. And the method we use in our group is called diffusion Monte Carlo. Basically, how it works is that if you replace the real time t in the Schrodinger equation with imaginary time tau equals it, it turns the Schrodinger equation into a combination of diffusion and growth decay equations. And here I have an animation to show how this process works. As you can see that at the beginning of the simulation, all the walkers are the same position, which means they all have the same configuration. And once the simulation starts to run, the walker is going to start to diffuse and also either die or make copies of itself, depends on its potential energy. And as you can see at the end of the simulation, the distribution of the walker is pretty similar to the analytic solution, the ground state wave function of the system. And this method is pretty precise, but it's very expensive. Because if you think about it, if we have 100,000 walkers propagating for 10,000 time steps, that's a total of 1 billion potential evaluations. And as the system gets larger, it can take forever, like years, to get a good result from this simulation. So how could a neural network help us facilitate this process? Well, first of all, neural network is GPU-based, which allows massive parallelization, which just means all the potential energy evaluations of all walkers can happen at the same time. And also, for each potential energy evaluation, it only involves simple and fast linear transformations, which makes it extremely fast. And how this process works is that we start with running a small-scale diffusion Monte Carlo simulation with small amount of walkers and time steps to just collect training data. And then we use that data to train a neural network to learn how to predict energies based on configurations. And after that's done, we can run large-scale diffusion Monte Carlo with a neural network potential energy surface. And we tested this method on 3 systems, which are water monomer and also CH5+, which is protonated methane, and also water dimer. And as you can see here, when we have 1 million walkers for water dimer, the neural network potential energy evaluation is almost about 10 times faster than the conventional method, which is great. And as the system gets larger and larger, the neural network is even going to get faster and faster comparatively. So now we know that neural network is fast, but is it accurate? Here I'm showing some results from the CH5+ model. And the left 2 plots here basically shows how accurate the neural network is able to predict the potential energy. The x-axis here is the correct potential energy for that configuration, and the y-axis is the energy predicted by the neural network. And as you can see that they agree with each other pretty well. And for the top plot here, it shows the distribution of errors. And you can see that basically all errors are within 1% of potential energy. And the right plot here is the ground state wave function of all HCH angles of CH5+. And as you can see that here, so the blue plot is the Bowman surface, which is the conventional method. And you can see that neural network agrees with it perfectly. And so does the 0-point energy here. So that's the work I've done so far. And our future directions are, first, we're going to move on to larger systems. Like I've just started this project with water hexamer. And also we're going to train neural networks with initial data to explore systems with no existing fitted potential energy surfaces. And at last, thanks to everyone in the McCoy group, and special thanks to Ryan for all his help and support to get my first paper ever published. And thank you, everyone.